Hello everyone, I'm Takasumi Tanabe from Keio University. First of all, I would like to thank the IEICE committee for giving me this opportunity to present at this English seminar. In this talk, I will explain about the fundamentals and recent advances in microresonator frequency combs, commonly referred to as microcombs, and their applications in optical signal processing. As I will show in this talk, microcombs are emerging as powerful tools that are pushing the frontiers of communication, sensing, and computation. Let me begin by outlining today's presentation. First, I will explain why microcombs are promising candidates for optical signal processing. Next, I will introduce the fundamentals, characteristics, and generation mechanisms. Following that, I will discuss key application areas including optical communications and terahertz wave generation. Finally, I will present our latest work on applying microcombs for optical convolution operations, demonstrating that microcombs are indeed powerful devices for signal processing and a key enabler for future photonic AI technologies. Let's begin with some background on frequency combs and why they matter in photonics. This slide explained what a frequency comb is. A frequency comb is a light source where spectrum consists of evenly spaced longitudinal modes in the frequency domain, resembling the teeth of a comb. That's where the name comes from. In the strict sense, it refers to sources whose mode frequencies are precisely known, requiring control over the carrier envelope offset frequency or FCEO. This is typically achieved through F2-2F interferometry. However, the definition has broadened in recent years. Mode-locked lasers with well-defined phase-locked longitudinal modes are now also considered frequency combs, providing the space is large enough to be resolved with standard spectrum analyzers. Importantly, optical frequency combs act like gears that link microwave and optical domains. This ability to bridge vastly different frequency scales is critical in precision methodology and signal processing. As we can see in the diagram, microcombs make it possible to seamlessly translate between microwave, terahertz, and optical frequencies, enabling compact and highly integrated systems. Here we compare traditional frequency combs, such as those generated by titanium, sapphire, or fiber lasers, with microresonator-based frequency combs. Conventional comb sources are typically large, expensive, and have low repetition rates. In contrast, microcombs are compact, cost-effective, and operate at much higher repetition rates, making them ideal for integrated and scalable applications. They have already been adopted in areas like LiDAR, spectroscopy, and astronomy, especially where integration and high repetition rates are essential. The figure here illustrates the range of achievable repetition rates. Microcombs can exceed gigahertz repetition rates, which are difficult to reach with other technologies. So why do microcombs matter? They support a wide variety of applications: ultra-high capacity optical communications, low phase noise terahertz wave generation, precision LiDAR systems, optical clocks, and even quantum information processing. Recent reports have demonstrated data rates over 55 terabits per second using microcombs, and applications like astrocoms and optical frequency standards continue to advance. This broad utility demonstrates their significance as a foundational photonic platform. Over time, frequency comb technology has gone through three major generations. The first relied on bulk solid-state lasers, the second introduced fiber-based approaches. Now, the third generation, microcombs, features chip-scale integration and large free spectral range. These characteristics lead to a well-spaced longitudinal modes well suited for advanced and practical applications. Let me explain one of the practical use cases. Microcombs can act as multi-wavelength light source, making them ideal for wavelength division multiplexing in optical communications. Compared to conventional distributed feedback laser arrays, microcombs offer significantly lower power consumption. For instance, DFB lasers consume about 2 watts each because it requires individual temperature control. To cover the C-band with 160 channels at 25 GHz spacing, we need total of about 320 watts. A microcomb system achieves similar channel coverage with just 70 watts, even accounting the pump amplification. Recent developments even suggest EDFA-less operation, which could further reduce power consumption. This is a major benefit for energy-conscious data centers and telecom infrastructure. Another key advantage of microcombs is the ability to perform matrix operations, which are central to neural networks and AI computing. This slide shows how microcombs enable matrix vector multiplication using wavelengths, time, and spatial multiplexing. Each matrix element can be encoded independently across different wavelengths or time delays, avoiding crosstalk, and summed in optical domain using photodetectors. This multiplexed processing is inherently parallel and enables high-efficient, scalable photonic acceleration for AI workloads. To briefly summarize the core advantage of microcombs. First, they offer large longitudinal mode spacing from 10 to 300 GHz, making them suitable for a variety of signal processing tasks. Second, they are easy to integrate with photonic platforms like silicon nitride or 3-5 semiconductors. And most importantly, they enable energy-efficient generation of many coherent wavelengths at once. Although the full potential of coherence across modes is still under exploration, microcombs are already proving to be key components in scalable, low-power photonic systems. This timeline shows the evolution of microcomb research. The first demonstration of cocombs was in 2008, followed by soliton microcombs in 2014. By 2016, self-referencing techniques emerged, and in 2020, turnkey microcombs became available. This last milestone, turnkey in operation, is particularly significant as it makes microcombs user-friendly and ready for real-world applications. This slide presents a comprehensive roadmap for microcomb applications, ranging from optical communications and terahertz systems to LiDAR spectroscopy and space technologies. It outlines projected improvements in output power, phase noise, and integration by 2040. The roadmap emphasizes the critical role of continued R&D, especially in materials like silicon nitride and hybrid 3-5 platforms. Further details can be found in the public roadmap published by the CompSquare Consortium, which I currently chair. Now let's move into the technical core of today's talk, starting with the fundamental principles and generation methods of microcombs, followed by their practical applications. Various method, various materials and platforms are used for high-Q microresonators. Silicon nitride is well suited for integrations, while crystalline materials like magnesium fluoride offer exceptionally low thermal noise, therefore suited for metrology applications. Diamond and silicon enable transparency in the infrared region, and silica remains a major stable choice. These material platforms allow us to optimize microcombs for different use cases. For more detail, please refer to our publication in Laser Kenkyu. Microcombs are generated via third-order nonlinear effects inside high-Q microcavities. When a CW continuous wave laser is coupled into the microresonator, strong optical confinement enables four-wave mixing. Because the resonator supports nearly equidistant longitudinal modes, degenerate and non-degenerate four-wave mixing process generate new frequency components at those modes. The resulting broad spectrum, as shown in our experiment with a silica microtoroid, can be used for various applications. In this case, the phase of each mode is not locked, but if phase locking is achieved, the output becomes pulsed. This is known as the soliton state. To achieve a stable soliton state, we must carefully balance both amplitude and phase in the cavity. This means balancing cavity loss with input power, and balancing phase modulation caused by dispersion and Kerr nonlinearity. This behavior is described by the Lugiato-Leveva equation. Intuitively, to counteract the phase shift induced by the Kerr effect, we require anomalous dispersion in the resonator to maintain the proper soliton phase condition. Dispersion, therefore, is a key parameter. Here, we show simulation results for silicon nitride waveguides. By adjusting the waveguide width and height, we can engineer anomalous dispersion. In this example, a width of 1400 nanometer and a height of 800 nanometer gives optimal dispersion when using a silica cladding. However, there is a challenge. This waveguide dimension supports multiple modes. As I'll show on the next slide, multimode behavior can introduce mode coupling, which disturbs dispersion uniformity. This is a measured transmission spectrum for a fabricated silicon nitride microcomb. Ideally, we would see uniform dips across all wavelengths, but instead we observe shallow dips at specific regions. From the mode spacing, we can derive the group delay dispersion and plot it as a function of mode number. Although overall anomalous dispersion is achieved, local modulation or local fluctuation occur due to the mode coupling between the fundamental and higher order mode. This anti-crossing effect causes resonance shifts appearing as local dispersion modulation. Therefore, careful waveguide design and simulation are essential for reliable soliton generation. Once we have dispersion engineered devices, the next step is to initiate soliton generation. Simply injecting a pump laser is not sufficient. We need to scan the pump wavelengths along the resonance of the cavity. Microresonators are inherently bistable, and the Kerr effect causes resonance shifts during scanning, as shown by this illustration. As the pump approaches the resonance, the system may enter unstable chaotic regimes known as modulation instability. Soliton formation only occurs when the pump is located on the redly tuned side of the resonance. This process often starts with multiple solitons, and with continued tuning, a single soliton state may emerge, at which point scanning must be stopped to maintain it. This technique is known as the wavelength scan method. In real experiment, thermal effects further complicate control, making stabilization more challenging. This experiment uses magnesium fluoride whispering gallery mode resonators. By tuning the blue detuned to red detuned side of the resonance, the system transits through Turing patterns and modulation instability into dissipative core soliton states. The resulting output matches the expected thick square-shaped spectrum and supports femtosecond pulse generation. Another method to generate solitons in the pulse is the power scan method. Due to hysteresis, gradually increasing and decreasing pump power enables transitions from modulation instability to multi and single soliton states. Although we theoretically proposed this technique in 2016, it was difficult to stabilize due to thermal effects. Recently, a modified version called the power kick method was demonstrated, where rapid control changes help overcome thermal limitations by actively tuning the thermal optic response. The power kick method is especially effective in integrated silicon nitride microcombs, microresonators. A fast rise and fall in pump power triggers stable soliton formation. The generated combs has a repetition frequency of this particular case, about 300 GHz, and a clean ZEC square spectral envelope, making it ideal for compact, high-speed applications. This slide shows practical packaging for silicon nitride microcomb chips. Glass holders and fiber arrays with up to 78 cores are used for stable and scalable coupling. Both single-end and dual-end packaging designs are shown, which are essential for real-world development and testing. With packaged device ready, we conducted a 40-kilometer transmission test. We used a soliton microcomb as the light source without using any forward error correction. With a 400 GHz free spectral range and a quality factor of 1.5 million, this system demonstrated robust, high capacity optical transmission, ideal for short to mid-range telecom links. Here I present our results on massively parallel optical communication using a soliton microcomb generation by a silicon nitride microring. This slide shows the optical spectrum of the comb, covering the entire C-band with over 100 wavelength channels spaced at 400 GHz. Maybe not 100, but a lot of number of wavelengths, I mean. The smooth envelope conforms a soliton state. We used this comb in an IMDD system with simple on-off keying. Despite this basic configuration, the system achieved excellent transmission performance. The two graphs shows bit error rates. The left is after the left is back to back, and the right is after 40 kilometer transmission. And the bit error rate for all channels stay well below the FEA, forward error correction threshold, with many reaching below 10 to the minus 10, indicating nearly error-free performance. Above the graphs, we show eye diagrams for several wavelengths, all showing clean open eyes. This confirms that one microcomb can replace hundreds of DFB lasers, drastically reducing power and complexity while enabling high-capacity WDM transmission, even with simple modulation format. This slide presents a real-world field demonstration of our microcomb-based transmission system. We stepped outside the lab and used a commercial fiber link between Keio Yagami and K2 campuses to validate its practical performance. The setup used a basic IMDD scheme. A signal was sent from Yagami to K2 and looped back, traveling about 9 kilometers. In this configuration, we measured an excess delay of 3.1 microseconds. At first glance, that may not sound significant, but it actually highlights a major strength of microcombs in enabling low latency network. Conventional systems often rely on high spectral efficiency and digital coherent processing to reduce the number of lasers, but that approach adds both complexity and latency. With microcombs, on the other hand, we can generate hundreds of wavelengths from a single chip, allowing lower power per channel data rates, while maintaining total capacity. This makes it possible to eliminate digital signal processing altogether and use simpler analog transmission with minimal latency. In this sense, microcombs allow us to rethink network design. This demonstration shows that such a system is not just technically feasible, but also practical using existing telecom infrastructure. This video shows a demonstration of real-time robot arm synchronization between our two campuses. One robot arm is located at K2 campus, the other at Yagami. Microcombs were used to generate stable optical channels at both ends. By using a single optical wavelength at each campus for synchronization, we achieved perfectly matched motion between the two arms in real time. There was no observable lag, even though they were physically separated by several kilometers. This experiment highlights the potential of microcombs for enabling low latency, high stability communication. Such capabilities are essential for future applications like remote robotics, teleoperation, and immersive VR streaming. Next, I'd like to talk about wireless applications that microcombs can enable. The ITU has allocated spectrum between 275 and towards 475 GHz for next generation use cases such as vehicle-to-everything communication, high-speed links for aircraft, and smart factory automation. To access these bands, we need low noise sources at sub-terahertz frequencies. Microcombs, with their high repetition rates and coherent properties, are ideal candidates for generating signal in this range. This opens up exciting opportunities for photonics to contribute directly to 6G and beyond. Electronic approaches to terahertz wave generation face fundamental limitations, especially in phase noise. Typically, signals are multiplied up from lower frequency oscillators, which also amplifies the phase noise. In contrast, photonics can generate terahertz signals by directly down-converting from optical frequencies, where noise performance is inherently better. Microcombs are especially suited for this because the repetition rates fall in the sub-terahertz regime, naturally linking optical and terahertz domains. This graph compares phase noise from electronics and photonic systems. As you can see, photonic techniques, particularly those using microcombs, achieve more than 20 dB of improvement. In addition to lower phase noise, the photonic approach also enables more flexible functionality at terahertz frequencies such as modulation and multiplexing. For these reasons, microcombs are among the most promising technologies for opening up this frequency frontier. As a first step in this direction, we conducted a 300 GHz QPSK transmission experiment using a microcomb as the carrier source. In this setup, we select two comm lines. One serves as a signal and the other as a reference to create 300 GHz beat. After modulating one of the lines, the two are combined and injected into a UTCPD, Uni-Traveling Carrier Photodiode, which generates the RF signal, the terahertz signal. The 300 GHz wave is transmitted through a short waveguide and then received by mixing with a local oscillator. This simple setup confirms the feasibility of microcomb-based photonic transmitters at ultra-high frequencies. This slide shows the experimental result. The constellation map, the constellation diagrams, and error vector magnitude measurement for 5 and 10 gigabit per second QPSK signals demonstrate very clean and stable performance. The symbols are clearly separated with minimal distortion, indicating that the microcomb provides a highly coherent and stable carrier for terahertz modulation. Here we plot the bit error rates as a function of received power. In all cases, we achieved bit error rate below 10 to the minus 6, which is acceptable for most high-speed wireless systems. The center graph shows the assumed phase noise for analysis, ranging from minus 100 to minus 120 dBc per hertz at large offset frequencies. We ran a simple simulation to estimate how different phase noise levels affect the constellation. As expected, lower phase noise achieved only with microcomb technology, lower phase noise that can be achieved only with microcomb technology leads to better EVM and lower bit error rates. The graph on the right shows the actual measured phase noise from our system, confirming that microcombs provide a significant advantage. These results support the viability of microcomb-based photonic systems for future high-speed wireless communication in the 300 GHz band. To summarize this section, dispersion engineering is a key for obtaining stable microcombs. Silicon nitride offers high Q factors, low loss, and excellent integration with photonic platforms. Microcombs can serve not only as coherent WDM wavelength division multiplexing light sources, but also as carriers for high-frequency RF generation. This makes them highly attractive for future advanced communication systems, both in the optical domain and in emerging sub-terahertz wireless links. Excuse me. Now, let's move into the final part of my talk, where I will introduce our recent work on optical convolution processing using microcombs. This represents a highly promising convergence of photonics and computing, offering a new architecture for accelerating AI workloads. By increasing scalability and energy efficiency of optical systems, we can tackle the growing demands for machine learning with far less power than conventional electronics. As AI models grow in scale, the computational and energy demands are skyrocketing. For example, models like GPT-3 now exceed 1 trillion parameters. The graph shown here illustrates how the number of parameters has been increasing by a factor of 20 per year, while hardware performance, particularly GPUs, only doubles annually. This gap between software demands and hardware capabilities is becoming unsustainable. Moreover, AI performance follows a scaling law where improved accuracy becomes at the cost of exponentially greater power consumption. Power consumption is a serious concern. Training large models today requires over 900 megawatts hour, which is more than 5% of the annual energy consumption of all data centers in Japan. Clearly, we need a new direction for AI computing. That's where photonic computing comes in. Optical operations can be performed with extremely low energy consumption, on the order of attojoules to femtojoules per operation. Recent advances in photonic tensor cores, such as those based on Mach standard interferometers or microring resonators arrays, have shown that optical matrix multiplication is not just feasible, but highly efficient. This potential is already being recognized by the private sector. In the US, companies like Light Matter and Escape Photonics have raised hundreds of millions of dollars to commercialize photonic AI hardware. Investors, and researchers are clearly betting on applications. Momentum is building rapidly towards photonics as a scalable platform for next-generation AI infrastructure. And people believe microcombs will play a central role in that transition. This chart shows the matrix size required to support real AI tasks. For example, GPT-3 involves matrix size with more than 100 and 150 million elements. Scaling to this level is a major challenge for current photonic processors. Let's say we have a 64 x 64 photonic processor. It would require thousands of parallel units to handle GPT-3 level models. That's not practical with current integration technology. So we need a photonic architecture that can scale not just in spatial dimensions, but also along the temporal axis and of course toward the wavelength axis. For applications like large language model, LLE, large language model interface, or exposure estimation, we estimate that a configuration such as 128 times 128 times L, or even 8 times 8 times 1 million, where L represents time division multiplexing, would be able to support tasks like machine learning using Japanese board. This concept gives us a roadmap toward building scalable photonic cores capable of handling real-world AI workloads. Let me now introduce a key optical signal processing method, optical convolution, and how microcombs make it possible. Integrated microcombs can serve as multi-wavelength source for encoding filter widths across different wavelengths. Each wavelength experiences a different delay in dispersive medium, and all signals are integrated at photodetectors to produce the convolution results. On the other hand, optical heterodioning allows us to generate 300 GHz signals, forming a high-frequency wireless I/O interface. By combining optical processing and terahertz wireless transmission, we can create an end-to-end photonic system, one that's fast, power efficient, and overcomes the classical von Neumann bottleneck, where the I/O speed limits overall system performance. So we want to combine those two techniques. So first, let me explain the principle of photonic convolution in a bit more detail. Okay? We begin with a 2D image and flatten it into a one-dimensional signal. The corner filter widths are encoded into the intensity of each comb line, so each wavelength represents one filter coefficient. The one-dimensional signal is modulated onto an optical carrier using an electro-optic modulator. Then, the signal passes through a dispersive fiber, which introduces a frequency-dependent delay, as shown by here, or chirp, so that each wavelength is delayed differently. This chirp aligns the input signal in time such that the widened sum of overlapping elements occurs within a single time slot. At the photodetector, these delayed components are naturally integrated, producing the convolution output without requiring digital computation. It's fast, low latency, and scalable. This slide shows our experimental setup for implementing photonic convolution using a soliton microcomb. In the first part of the setup, we generate the soliton comb. Once the soliton state is achieved, we remove the residual pump light using a fiber back rating so that only the comb lines are sent into the convolution system. The input image is encoded using a lithium niobate modulator, and the corner filter is applied using a wavelength selective switch, which adjusts the amplitudes of individual comb lines according to the filter width. The spectrum shows here is a soliton comb used in this experiment. This figure represents the input image, and this one shows the filter pattern applied to the comb. Here are the results of the optical convolution experiment. The image on the left shows the output obtained from a standard digital convolution run on a PC. The center image is the result of our photonic convolution. The image on the right shows the difference, or error, between the two. We had only 2 bits errors out of 756 bits, giving an error rate of just 0.26%. This close agreement validates that our optical implementation matched the digital output very closely demonstrating that photonic convolution is both accurate and reliable. This slide compares the computational complexity of digital versus optical convolution. In our setup, we achieve a 23.1% reduction in computational load using optical processing. While the difference is modest for small datasets, the benefits scale dramatically as the number of images increases. As shown in this graph, once we reach large-scale workloads, the performance gap between digital and optical convolution widens significantly. This illustrates the real advantage of using photonic processors, especially for future AI workloads that demand both speed and efficiency. Next, we demonstrated I/O using 300 GHz wireless signals. The output from optical convolution operation was modulated on a 300 GHz carrier and transmitted to a different component. This setup uses zero bias detectors and high-speed photodiodes to convert the optical signal into a radio frequency signal. In this experiment, the convolution was performed using two signal comm lines, and the result was modulated using 3 reference comm lines. The resulting radio waves were then transmitted through a waveguide. Let me briefly explain the theoretical principle behind this process. We use odd-numbered comm lines to represent reference signals, and evenly numbered lines for signal path. When these optical signals are injected into a unitraveling carrier photodiode, UTCPD, their interference will produce a radio frequency beat signal. While I won't go into the full mathematical derivation here, the key idea is that this beat signal carries the result of the optical convolution. This slide presents the experimental result. In figure A, we see the outcome when the input image was modulated into radio waves and transmitted without convolution. Figure B shows the case where we performed convolution optically. They modulated the result on a 300 GHz wave transmission. Figure C shows the ideal convolution result computed on a PC for reference. The comparison shows that the optical convolution result was successfully transmitted wirelessly. However, we did observe some deviation between the optical and digital results. This discrepancy is mainly due to the phase fluctuation caused by optical path length fluctuation between the signal and reference channels. We plan to address this issue through future integration to ensure tighter optical path matching and improved stability. To summarize this section, we successfully implemented optical convolution using a soliton comm generation by a silicon nitride ring resonator. This allowed us to reduce the computational load by over 23%, and we demonstrated that the result can be modulated on a 300 GHz carrier and transmitted wirelessly. This work expands the role of photonic AI accelerators, not just handling the computation, but also performing low latency input-output, potentially solving system bottlenecks like the von Neumann limit. Let me conclude the whole presentation. First, I reviewed why microcombs are highly promising for optical signal processing. I explored the fundamentals, the generation mechanism, and their applications, from optical communication to 300 GHz wireless transmission. I also introduced novel application, optical convolution processing using microcombs, and demonstrated its potential for integration with terahertz wireless systems. I believe this represents a new and exciting direction for energy-efficient, scalable AI acceleration using photonics. Thank you very much for your attention.
Welcome to IEICE's new multilingual translation platform for our web services. IEICE publishes 9 peer-reviewed journals monthly in Japanese and English. This multilingual translation platform currently features 4 English-language journals. During the trial period, anyone can access this high-performance service. To start, visit the IEICE website, to the right of the slider, or go to Transactions Browse Multilingual Translation Trial site. The page displays 5 supported journals and top 10 most accessed papers from 2023 and 2022. To translate, select your preferred language from the flag icon on the top right. Let's choose Simplified Chinese. The page instantly translates, with paper titles now in Chinese. Notably, proper nouns like IEICE transactions, 6G and 5G, remain unchanged. Let's take a closer look at the top-ranked paper. The author's names, acronyms like AI, ML, Beyond 5G, and proper nouns are not translated. Unlike many journal sites that offer PDFs, this service provides full HTML with formulas, making multilingual translation possible. Found an interesting paper? Want to share it? Use the share icon to spread the word. Hover over the share icon to see 4 options: email, Facebook, X, and Line. Let's click the email icon. It auto-generates an email with the paper's title and DOI for easy sharing. You can also share via Facebook, X, or Line. For more details on this advanced platform, click the How It Works tab. Experience IEICE's cutting-edge multilingual translation platform and boost the global impact of academic research.